Hi, I'm Aaron Skrimsky. I'm a PhD student in the Stanford Biomechatronics Lab, and I'll be talking today about some recent simulation work on optimal control of an energy recycling actuator for mobile robotics applications. So the motivation behind this project is high efficiency actuation for low work tasks. So many useful robotic tasks, especially cyclical ones, don't inherently require high energy expenditure. And this includes things like pick and place tasks, robotic locomotion, and in some cases even prosthesis and exoskeleton assistance. So here, low efficiency leads to short battery life and larger batteries. And for something like a prosthetic device, we want it to be lightweight, so it should have small batteries, but we also want it to be able to run all day without needing to be recharged. So one really simple approach to improve system efficiency and reduce power consumption is to just add a spring in parallel with the motor. So we have here on the left is just a motor, and on the right is a motor with a spring. And they're performing the same task of raising and lowering a robot arm following a specific trajectory. And we can see that adding this just plain spring really reduces the total power consumption. The problem we run into is that a passive spring doesn't allow for control. So even though in this case adding the spring may help, for another task that we want this robot arm to do, the motor might have to fight against the spring and actually use more energy. So our solution to this is to come up with a scenario where we can have active control of a passive spring. So we can have the spring in an on state, like on the previous slide, where the spring is connected to the output, it's applying a force, and it's exchanging energy. But we can also take the spring and turn it off, where we disconnect it from the output, we connect it to the robot frame, and it just maintains its elastic energy and stays in place. And what makes this possible is some recent work out of our lab, which is the electroadhesive clutch. So shown here is an electroadhesive clutch. And when it's in the off state, if you pull on it, it moves. It doesn't resist the force. But when you apply a high voltage differential between the two halves of this clutch, it can withstand an incredibly high force. And these electroadhesive clutches have about a 10 times improvement in force per weight and about 1,000 times improvement in force per power consumption when compared to more conventional electromagnetic or magnetorheological clutches. So we can take a planar spring and put it in series with two of these electroadhesive clutches, and this allows the spring to be clutched in these two different configurations. And we can understand how this might be useful by walking through a very simple scenario where, in this case, our output clutch is connected to a mass and we're raising it against gravity. And in this example, we'll consider gravity as being off to the right. So initially, we have energy stored in our spring, and the spring is connected to the frame. If we connect the spring to the output and disconnect it from the frame, we'll initially exert a high force, and then we'll lift this mass up. So we lose energy in the spring, which gets converted to gravitational potential energy and kinetic energy. Now, eventually, the mass falls back down. We recapture this energy as elastic energy. And now, by taking the spring and reconnecting it to the frame and disconnecting it from the output, we end up back where we started. So we used a very small amount of energy in activating these clutches, but we've raised and lowered a mass in this process. So now we can take this configuration and stack a bunch of these clutch springs together in parallel. And this is what we refer to as the energy recycling actuator configuration. So by taking all of our outputs and connecting them to the same output shaft, we can actively control the amount of torque on the shaft just by choosing which springs we engage. So we can actively control force but using a very small amount of power. So we can also add a motor to this configuration. This improves our torque resolution because we can control the motor continuously, whereas we can only control the springs discretely, but it also allows us to now do net positive work and make up for any losses in our system. So this is the energy recycling actuator configuration. Now that we have this laid out, we can get into what is our optimal control problem. So we start off here with our objective, which is given some prescribed trajectory, we want to track a desired torque with minimal power consumption. And this is similar to how we might structure the control problem for an exoskeleton, where the trajectory is being dictated by the user's movement, and we want to supply a specific assistive torque. So the first part of this control problem is our control inputs. So we have a binary clutch control vector, so this is which springs are connected to the output and which springs are connected to the frame. We'll use a 1 to denote that a spring is connected to the output and a 0 for it being connected to the frame. And then our other control input is our motor current, which affects our motor torque. Our state vector for this problem is going to just be the spring displacements. Here we'll consider a system with n springs, and then our cost, which is our power consumption, is the power consumed both by the motor and the power consumed by changing clutch states. So we're going to optimize this subject to our dynamics and our constraints. And our dynamics include that the springs that are connected to the output will move when the output moves, but the springs that are connected to the frame will just stay in place. We also have spring movement that occurs at the instant when clutch control is changed. This is due to the electrodes stretching slightly, which causes the springs to contract slightly and lose a small amount of elastic energy. Now we also have some constraints on this problem, which include balance on the spring displacement, balance on our motor voltage, and also limits on the motor joule heating. The last constraint is that we need to make our output torque match up with a desired torque. And our output torque consists of our spring torque. Here, this is a function of the clutch control vectors, so which springs are connected to the output, and also a function of the spring displacements. And then our motor torque model includes inertial torques, a switched gearbox efficiency model, and also accounts for motor coulomb friction. So ideally, what we have is a scenario where the spring torque approximately matches up with the total desired torque, and we only need to use the motor to make up for these small differences. And this will be much more efficient than trying to use the motor to provide a majority of the torque. So with this setup, one really simple approach that we might try is what's called a greedy approach. And in a greedy approach, we try to minimize our cost function just one step at a time. So we look one step in the future and come up with a control that has the lowest cost. And if we do this, we see it starts out really well. We actually have negative power consumption, but our behavior rapidly degrades over time. And the reason for this is we're not actually planning to keep enough elastic energy in these springs, so we lose a lot of energy to start, and then we don't have enough energy in the springs to make good control decisions. So a much more sophisticated approach is the receding horizon approach, or the model predictive control approach. In this approach, we optimize the clutch control for a horizon of n steps in the future, and then we apply the first control in the sequence and then replan. So we can write out our n-step objective like so, and then we add another term which tries to get our springs to be at some target position at the end of our planning horizon. This prevents us from losing a lot of elastic energy in the springs over time. So this resulting optimization problem is what's referred to as a mixed integer non-linear program. And what's hard about solving this is that we have a combinatorial blowup in the number of possible clutch control options. And this is exponential both in the number of springs we have and in the number of steps we're trying to plan. So our approach to solve this efficiently without trying to use a brute force method, which would be infeasible, is to use what's called mixed integer quadratic programming. So shown here is a regular quadratic program, and QPs are convex and can be solved very efficiently. Now when we add this additional constraint that some of the optimization variables can only be 0 or 1, this becomes a non-convex problem, which is a mixed integer quadratic program. But by exploiting the convex quadratic program subproblem structure, we can often solve these very efficiently. So what we're going to do is we're going to take our initial mixed integer nonlinear program and convert it to a mixed integer quadratic program by constructing an equivalent problem with new variables and new constraints. And one example of how we do this is when we have the nonlinear product of a binary and a continuous variable in our problem, we can introduce a new variable and 4 linear inequalities. So for example, with our spring torque, which is a function of both the clutch control vector and the spring displacements, we can introduce a new variable which is equivalent to the product of these two variables. We introduce 4 linear inequalities which ensure this equivalence relationship, and this allows us to write out the spring torque just as a linear function of this new variable. And we can use similar tricks for the product of two binary variables and for assigning a binary variable based on the outcome of an inequality. So how does this look when we try this MPC approach? We see that we have much better performance on the energy recycling actuator than we do for the motor alone or the motor with the parallel spring. But we also see that this behavior can work really well on a wide range of torque and displacement profiles. So here we have another trajectory, and on this one, the same passive parallel spring doesn't really provide that much benefit over the motor, but the energy recycling actuator configuration still uses much less electrical energy overall. So to really quantify how well this works, what we did is we generated 100 random zero network cyclical torque and displacement profiles. We optimized a motor and a spring for these profiles by optimizing over the entire maximum motor catalog, and then we compared the performance of just the motor and the spring to the energy recycling actuator. And we found that over these 100 test cases, the energy recycling actuator did better in all 100 test cases and used less than 50% total energy on average. So these are the results for the 100 cases sorted from left to right. And this exciting result really motivates our future hardware development on this project. I would like to thank a few people who've helped out, as well as our funding source. And if you have any questions on any of this, please feel free to email me. Thank you.